All right, so we're in 6.3, part 2. And that reminded me, for some reason, when I used to, at one point in my life, I delivered furniture, and I delivered a corner bookshelf to a dome house. And that was, I thought it was kind of a strange thing to have in a dome house, because there weren't any corners. All right. Some more vectors. So what we want to start today by talking about a little bit more about unit vectors. Unit vectors are very, very useful, very important, and they come up a lot when you're working with vectors. So first off, let's remember a unit vector. What do we mean when we're talking about a unit vector?
Length of 1.
Length of 1, magnitude 1. So that's why we call it unit vector. Its length is 1. The reason that unit vector is important is because if our length is 1, really all that the vector is just telling us a direction. You don't have to worry about how long it is. It's telling us a direction. So what we want to be able to do is find a unit vector in a specific direction. So if we have a vector, we want a unit vector in the same direction. So let's say we have a vector v. And we don't have to use the components, but we're going to say v is v1, v2. And we want a unit vector in the direction of v. So we want a vector of length 1 that's pointing in the direction of this vector. So our unit vector in the direction of v is, and I'm going to say u for unit vector. Basically, we just get rid of its length. So we divide the vector by its length. 1 over the magnitude of v times v. So we're dividing its length out of the vector. And the other way that you'll see this written is v over the length of v. Same thing. So we're taking this vector and we're just dividing its length out. So that gives us a unit vector in the same direction. And then what this lets us do is just work with the direction of v and not have to worry about its length. Couple of reasons we might want to do that. Say we have a cable, and we're interested in the tension in the cable, the force in the cable. Well, we know the direction of the cable, we know its angle, and we know the length of the cable, but we don't want the length of the cable mixed up in our problem. So we want the force in the cable. So the force in the cable is going to be in the direction of the cable, but we want the magnitude of our vector just to be the force and not have to do with the length. So that's when we would use a unit vector. We want a unit vector in the direction of that cable. So that would be one reason why we would use a unit vector. We'll talk a little bit more about unit vectors in just a second, but I want to do a calculation using unit vector. So this is our unit vector. We just divide by its length, divide a vector by its length. What if we wanted a vector of magnitude 10 in the direction of v? How would we find a vector of magnitude 10 in that direction? What would you say, David? We just multiply this by 10. the length of this vector is 1. If we want its magnitude to be 10, we just multiply it by 10. So we can make the magnitude now of this vector anything we want. So we can get a vector of any magnitude in this direction. So this lets us find the direction and then work with any magnitude we want. So let's do one quick calculation, one quick example, and we'll talk a little bit more about what we call standard unit vectors. So we want a unit vector in the direction of the vector 3, -4. And I'll call this vector v, since we've been calling our vectors v. So finding our unit vector, easy calculation. We're going to do v over the length of v. Didn't draw my v very well there. All right, so what is the length? If v is 3, -4, what's going to be the magnitude of v? 5. So one side of our triangle is 3, one side of our triangle is 4, so we have a 3, 4, 5 triangle. Thinking of vectors as little triangles can be very helpful. We always have an x magnitude, a y magnitude, and the vector itself. So we can always think of the vector as a little triangle. And if we think about little triangles, that should hopefully make us think about trigonometry. And we'll talk about how trigonometry and vectors come into play with each other in just a second. So the magnitude of our vector is 5. So our unit vector call it u, is 1/5 times 3, the vector 3, -4. And I could also write that as 3/5 -4/5. And if we checked, if we found the magnitude of this vector, we would see that it does come out to be 1. So there's our unit vector. We wanted a vector of magnitude 18 in the direction of this vector 3, -4. We multiply this by 18. If we wanted to be in the opposite direction, we'd multiply it by -1. So now we can have lots of different ways that we can work with this unit vector. We don't have its length mixed up with it anymore. Questions there? All right, so now that we know a little bit more about unit vectors, we have what we call standard unit vectors. And our standard unit vectors are just another way that we can work with vectors, just another notation that we can use for working with vectors. They can be very convenient depending on the kind of problem that you're doing. So we're going to say our standard unit vectors are I hat. I hat is the vector 1, 0. And j hat is the vector 0, 1. When we go into 3 dimensions, our unit vector in the 3rd dimension would be k hat. So we'd have I hat, j hat, and k hat. And all these are our unit vectors pointing in the x direction and a unit vector pointing in the y direction. So if we drew a picture on our axes, if we put these two standard unit vectors in standard position, draw little red vectors here. There would be I hat, and there would be j hat. I know I didn't make my magnitudes exactly the same. But if I drew these perfectly, I could do this. That looks a little better. Whoops, didn't want that arrow. There we go. I guess I could have left the arrow there, but I want it to match my other arrow. There we go. All right, so there's I hat and j hat. Just unit vectors in the x direction and unit vector in the y direction. And what this lets us do is we can take any vector if v is the vector v1, v2 in component form, we can say v equals v1 I hat plus v2 j hat. V units in the x direction, v1 units in the x direction, v2 units in the y direction. These two mean the same thing. They're just different notations for this vector. And we can write any vector in the plane as a combination of I hat and j hat. We just put the x component in front of I hat, the y component in front of j hat. We call this a linear combination of I hat and j hat. So what we say is we can write any vector in the plane as a linear combination of I hat and j hat. That's just a fancy way of saying take the x component and put it in front of I hat, take the y component and put it in front of j hat, and you have the same vector. So the way that you might be asked a problem with this in the homework, they'll say express v equals, and we'll use our 3, -4 vector as a linear combination of I hat and j hat. And all this is asking you to do is rewrite this as v equals 3 I hat minus 4 j hat. That's all that kind of questions asking. All of our operations with vectors that we talked about, addition, subtraction, multiplying by a scalar, same rules apply for using the standard unit vectors. Add or subtract the x components and the y components separately. Multiply by a scalar, multiply everything by the number. Nothing different, it's just kind of a different way of writing. You'll see this I hat, j hat in physics and engineering a lot. You'll see the bracket notation more in mathematics. So questions on our standard unit vectors? All right, so we've been talking about triangles, we've been talking about, and Ryan did our example up here, number 43, and he used cosines in the problem. We're going to talk about how vectors and trigonometry are related next. So that is what we call the direction angles. Our vectors are little triangles. We can think of our vectors as little triangles. Triangles lead to trigonometry. So let's draw our coordinate axes, and we'll put our vector in standard position. So here's our nice vector, standard position, and we're going to call this angle from the positive x-axis theta. And the coordinates of this point up here are x, y, and we'll call this, we'll say this is a unit vector. So the magnitude of u is 1. Okay. Anybody find wallet glasses? Is that what you said, Andrew?
Yeah.
I didn't see them at the end of the last class. If they show up, I'll give them to Miss Winger.
Yeah.
Okay? So we're going to say u is a unit vector. We're going to do just like we did when we talked about the unit circle, when we talked about trigonometry. So I'm going to project that down onto the x-axis. So if the magnitude of u equals 1, if the length of this hypotenuse of this right triangle is 1, what's this x component of u? How do we find this side of this triangle? Cosine theta, just like we did on the unit circle. Our hypotenuse is 1, our radius is 1, so this side of the triangle is cosine theta. And this side of the triangle would be what then? Sine theta. So we can write in component form, we would say u equals xy, but we can also say the x component is cosine theta. We could say u equals cosine theta sine theta. Or if we use I and j notation, we could say u equals cosine theta I plus sine theta j hat. So we can talk about the x component and the y component using this angle. And if we have a vector that's not a unit vector, so we're going to say that v equals the vector v1, v2. We can use the same idea, but rather than the hypotenuse being 1 unit long, the hypotenuse is going to be the magnitude of v. That's how long that's going to be. So we could say that v is going to be the vector magnitude of v cosine theta and magnitude of v sine theta. Using the same idea that we did here, but rather than our hypotenuse being 1, the hypotenuse is going to be the magnitude of our vector, or we write it in I hat j hat notation. This is going to be v magnitude of v cosine theta I hat plus the magnitude of v sine theta j hat. And if we only knew the x and the y coordinates, these two sides of the triangle, how would we find the angle? How could we figure out the angle? So let me draw a picture here. So this is v. And this component is v1, and the y component is v2, and that's theta. How would we find theta there? If all we knew is v1 and v2. Tangent of theta is v2 over v1. So theta would be the inverse tangent of v2 over v1. The inverse tangent of y over x. So that's how we would find our angle if we only knew the two components of our vector. Inverse tangent of v2 over v1. Inverse tangent of y over x. Just like we did when we were working with trigonometry. So questions here. So bottom line here, all we're doing is thinking about these vectors as little triangles. And we can treat them just like little triangles and use trigonometry on the vectors just like we used on triangles. Same kind of idea. All right, so what I want to do is an easy example talking about these angles and then talk about some applications. We'll do a couple of application problems that have to do with vectors. All right, so the easy problem first. We want the direction angle of the vector v equals 2I minus j. So we're going to say that theta is the inverse tangent of y over x of -1/2. So we plug that into our calculator, we get theta is, when we plug that in, we get negative 26.57 degrees. Yeah, it is. Usually in vectors you're in degree mode. Yeah. So let's draw a quick picture here. Here's 2I minus j over 2 and down 1. So here's my vector. What we found was this angle. 26.57 degrees. In standard position, how do we normally measure our angle? Counterclockwise from the positive x-axis. So normally we're looking for that angle. So if we have this angle as 26.57 degrees, how would we find this angle in standard position? Subtract this angle from 360. So standard position, theta is going to be 360 degrees minus 26.57 degrees, and we would get 333.4 degrees. So in standard position, our angle we'd say the angle is 333.4 degrees. So that's how we find our direction angle. In general, when you use your calculator, when we use the inverse tangent, thinking about our domain restriction when we found our inverse tangent function, what's our calculator going to give us an angle between which two angles? Remember our restriction for inverse tangent? Quadrant 1 and quadrant 4. So our calculator is going to give us an angle between negative pi over 2 and pi over 2, or negative 90 degrees and positive 90 degrees. So in general, you're going to have to look at the signs on your x and your y coordinate to decide which quadrant you're in to find your angle in standard position. So if we're in the second quadrant, we'd be over here somewhere. Third quadrant, we'd be over here somewhere. And you have to take that into account when you're finding your angle and if you want to express it in standard position. All right, questions on that example? Okay, what I want to do next is a couple of applications problems. There's several kinds of applications problems in your homework. Most of them most of the problems are just kind of straightforward problems, but there are a few application problems. So I want to look at a couple of those, just setting them up. Questions before we go on? Okay. So for this problem, we have a piano. And we are, it weighs 500 pounds. And we want to push it up a ramp. And the ramp is at 30 degrees with the horizontal. And the board that we're using our board, the salesman at Home Depot says this board will hold 450 pounds. So the board will support 450 pounds. We want to know, will this work? So let's draw a picture. So here's our ramp. Here's our piano sitting on the ramp. That's the back. It's an upright piano. That's the back of the piano. That angle is 30 degrees. So when we say the piano weighs 500 pounds, which direction is our vector that's talking about the weight of the piano going to point? Caleb holding his pen like this. Straight down. Our weight always goes straight down. So if we're going to draw the weight as a vector, our weight looks like this. And that magnitude is 500 pounds. In the English system, for those of you that are in physics, English, pounds is a measure of force rather than mass. So we don't have to do anything with the acceleration due to gravity. When we say that the board can support 450 pounds, which direction is the board supporting the weight? What's that? So you had the right idea. The weight that the board can support, if we said the board can support 450 pounds, is it supporting 450 pounds? If I said the top of this table could support 450 pounds, am I saying it can support it sideways? No. Straight into the table, right? We can support 450 pounds. If we apply 450 pounds of force perpendicular to the table, that's what it can support. So we're saying that we're interested in this portion, the amount of weight that this piano is exerting, the amount of force that it's exerting at a 90-degree angle to the board. So we want to see if that component, that portion of this force, is larger or smaller than 450 pounds. So we're going to have a force being exerted on the board, and we're also going to have to exert a force directly up the ramp to keep the piano from sliding down the ramp. So this is our picture, and we want to see, is this larger or smaller than 450 degrees? All right, so if this angle is 30 degrees, what is this angle going to be? If this angle is 30 degrees, what's this angle going to be? This one's 30. This one's also going to be 30. And we want to find the magnitude of this vector, and I'm going to label it x. It's our unknown. So looking at this little triangle, let me redraw that triangle. That's 500. That's 30 degrees and that's x. So looking at this triangle, and this is a 90-degree angle. How are we going to find x here? Which sides of the triangle, this right triangle, do we have compared relative to this angle? The adjacent and the hypotenuse. So we're going to use cosine, SOHCAHTOA, adjacent, hypotenuse. So we're going to say that x equals 300 cosine 30 degrees. Cosine of 30 is the adjacent x over 500, so that gives us this. So x equals 300. What's the cosine of 30 degrees? Square root of 3 over 2, unit circle. So x equals, why did I write 300? Thank you. I think I was thinking 30 degrees. 30 degrees, that's equal 3 from the 30 degrees. 500, thank you. So we get 250 square root of 3. Plug that in to my calculator, and that's approximately 433 pounds. So the board will support our piano. Barely. What if the problem asks us how much force we would have to apply pushing along the ramp to keep it from sliding backwards? How would we figure that out? So we're talking about this piece. What do you think, Daisy? Right, so we want this one instead. Right, so we're finding this rather than x. So how can we do that? I heard someone say sine. So question mark equals 500 sine 30 degrees. Sine of 30 degrees is 1/2. 250 pounds. So we'd have to apply 250 pounds of force to hold that piano from sliding down the ramp. And we're saying that the ramp is somehow we would have to supply 250 pounds of force. There's enough friction in the wood. That friction, the force of friction, might hold it back. Otherwise, we'd have to have some strong people pushing on it. So our board will support the piano. We'd have to push on it with 250 pounds of force to keep it from sliding down the ramp. I guess we could think of the piano being on really good roller blades, so we don't have to worry about friction.
You need 250 pounds of force just to keep it in one spot, and then you therefore need over 250 pounds of force to keep it moving forward.
All right, questions on that problem? Okay, let's look at one other. This one has to do with one of our favorite topics, bearing. A bearing problem. So for this one, we have a plane. And the bearing of our plane is south 60 degrees east at 600 miles per hour. And the wind is blowing at north 45 east at 80 miles per hour. We want the resultant speed and direction of the plane. And resultant, again, the resultant just means that we add all the vectors together. So we want the resultant speed and the resultant direction of the plane. So in general, when we have a problem like this, where we have two different things, we're looking for the resultant. We want to break our vectors into components. So we're going to use our components. So we're going to break our vectors into components, and then we add the components to get the resultant. So that's one nice thing about vectors, is we can break this apart, break it into pieces, and we work with the separate pieces. So first off, let's draw a picture. Here's my compass. And it says our plane is bearing south 60 degrees east. So our plane is flying this direction. And that angle is 60 degrees. And the magnitude of this vector is 600. So we're talking about our velocity vector. And now I'm going to draw another little compass here. Or we can draw it this way. Let's just draw it up here. Our wind is blowing at north 45 degrees east. So that's our bearing for our wind. And the magnitude of that velocity, the wind velocity, is 80. So we're going to break each piece into components and add the components. So let's start with the plane. And I'll call that vector P. So looking at this triangle down here that represents our plane, let's find the x component, the horizontal component of its speed. First off, if it's flying in this direction, let me redraw my arrow here, is the x component, is the horizontal component going to be positive or negative? Positive. Okay? So how do we find this side of this triangle? We have our 60-degree angle here. It's going to have to do with the sine of 60. Our magnitude of the hypotenuse is 600. So that's going to be 600 sine 60 degrees I hat. And our y component, our horizontal or vertical component, is it going to be positive or negative here? Negative, because we're flying towards the south. I'm going to put a minus. And how are we going to find this side of the triangle? 600 cosine 60. Perfect. There's our plane vector. And our wind. Let's find our wind vector. Call that W. For this triangle, I'm going to connect this down here. Just project this down here. X component, horizontal component, positive or negative? Positive, because the wind is blowing towards the east. So how are we going to find this side of this little triangle? If that's 45 degrees, that's also 45 degrees. So this side of the triangle is going to be cosine, and our magnitude is 80. And that's I hat. And the y, the vertical component, positive or negative here? What is it? Positive? Did you say positive? Yeah? Okay. Plus, and this is going to be given by the sine of the angle. So we get 80 sine 45 degrees. J hat. Now we can find our resultant vector. We just add these two together. So the resultant add the x components. So we get 600 sine 60 degrees plus 80 cosine 45 degrees times I hat. Plus, and I'll put this down here on the other line, negative 600 cosine 60 degrees plus 80 sine 45 degrees. And this is our j hat component. There's our resultant vector. Now we can calculate. Plug this into our calculator, get our I hat and our j hat component. So I'm going to say that our resultant, p plus w, when I plug this into my calculator, calculate this all out, I get 576.18 I hat minus 243.43 j hat. And this is where I messed up in the other class because I forgot this negative sign and I added these two together instead of subtracting this. So there's our resultant vector. Now what did the problem ask us to find? The resultant speed. So how do I find the speed? The magnitude. The speed is the magnitude. The velocity is the vector. The speed is the magnitude. So the speed is the square root of 576.18 squared plus 243.43 squared. And when I calculate that all out, I get, it's at about 625 miles per hour, 625.49 miles per hour. Does it make sense, looking back at our problem, does it make sense that with this wind blowing, it would be going faster? It's always good to see if what you came up with makes sense. Laura says yes. Why do you think yes, Laura? Right, so this horizontal component is blowing in the same direction that the plane is moving horizontally. So it's getting a little bit of a tailwind in the horizontal direction. Now the wind's blowing kind of against it in the vertical direction, but that's a pretty small compared to its overall speed. So it's getting a little boost in the horizontal direction. So it makes sense that it could be going a little bit faster. If we got that it was going way faster, 800 miles an hour, maybe we want to check our work. Or if we got that it was going way slower, like 200 miles an hour, we may want to check something. All right, so we're almost done. It says the problem asks us to find the resultant speed and direction. So let's draw another picture here. Here is our resultant vector. So our resultant speed is something like this. And this is 576.18. And that side of our triangle is 243.43. We can find theta here, right? How do we find this angle? Tangent, inverse tangent. So the tangent of the angle is the opposite over the adjacent. So theta is the inverse tangent of 243.43 over 576.18. Plug that in my calculator, and my calculator says that this is 22.9 degrees. So this angle is 22.9 degrees. Is that our bearing angle? Where do we measure bearing from? From the north-south line. So we're looking for this angle. So how are we going to find this angle? If we know this one, how do we find this one? So how did you find that, Daisy? 22.9. So these two have to add up to 90. So if we subtract from 90, 90 minus theta gives me what it 67.1. So this angle is 67.1 degrees. So our bearing, Daisy says south, 67.1 degrees. Whoops, degrees east. So our resultant speed, 625.49 miles per hour, at a bearing of south 67.1 east. Broke our vectors into components, added the components to get our resultant. Questions there? All right, there's one other kind of problem. I'm not going to do another example. I just want to mention this other kind of problem that there are a couple in your homework. I call them static problems. So the static problems are two things. You have like two cables, two cranes, two strings supporting a weight, and it wants you to find the tension in the cables. So just same kind of idea. Break your forces into components and add your components to get the resultant. The thing that you have to keep in mind with static problems is the vertical force has to support the weight of the object. So the resultant vertical force supports the weight. And because it's not moving, the horizontal forces have to balance. They have to be equal. They have to cancel each other out. So the horizontal forces I'm going to say balance or cancel. So whenever you have a static problem, all the vertical forces added together have to support the weight of whatever these things are holding up. And the horizontal forces, because it's not moving, it's not being pulled in one direction or the other, horizontal forces always have to balance. So when you're doing static problems, a lot of times you end up with two equations. You have to solve one equation for one variable and plug that into the other. Same kind of idea, break the forces into components, add the components, but in static problem the vertical supports the weight, the horizontal components balance or cancel. All right. Homework.